The microphone is somewhere here.
Microphone is somewhere.
Somewhere here in the
Okay. Okay. Good afternoon, everybody. Thank you for coming here in a lovely sunny day. For those who don't know me, my name is Ellen Du. I'm a professor in computer science and Atlas Institute. So it's given me doubly the pleasure to introduce Daniel Leithinger. I remember Daniel joined in 2018, and we are brainstorming what should his lab name be. We recognize that there's THING in there, those things, transforming human interfaces for the next generation. And we say, right. Okay, so Daniel is going to show a whole bunch of interesting stuff about transforming interfaces, and I will just let you take it away. Thank you.
Thank you so much, Ellen. Well, thanks for joining, everybody, and thanks for the lovely introduction, Ellen. So today I'll talk about things and about transforming. It's a bit of a long title, but designing elastic spaces with shape-changing and haptic interfaces, and that's pretty much summing up what me and my students have been inspired to do. And I'll start with inspiration. Let me just see where I can. There we go. So just look at this image, let it sink in for a little bit, and just think about everything that is going on here. This is, to me, very, very inspiring, this idea that, you know, we're creating, there's a child learning, there's material, the material keeps changing, and just thinking about all the sound, the smell, the tactile feedback that you get from the clay that is changing here, and also from the hands guiding. So I think this richness of interaction is what we should strive for in everything we do. And especially when it comes to using computers, because right now using computers is very devoid of this material richness and of engaging our body. So this, you know, image from Zoom times, we have all experienced. Some of you are experiencing it right now on Zoom. But to me, Malcolm McCullough paraphrases that, like paraphrased from his wonderful book, Abstracting Craft. Right now, still, when we talk about computers, eyes are in charge and hands are underemployed. And so I named this talk Elastic Spaces because I'm very inspired by the idea of using objects and environments that can physically reconfigure in order to let us engage with our body as we use computers. So elastic spaces actually is a term that was coined by Gianni Colombo when he did this installation here in Graz, which also happens to be in Austria, where I grew up. But so what elastic spaces was essentially this empty black space that was defined by these strings that were in this space. And as you were walking through as a participant, motors would keep reconfiguring, like pulling at those strings and reconfiguring the space. So it was like literally the environment you were in suddenly became to like keep changing. And I think that this is essentially the richness to me that we see in, like, you know, back in 1967, and a lot of related kinetic art by Group OT, which Gianni Colombo was part of, that we still don't really see. When we talk about computers and work right now, we're still thinking about a regular graphical user interface, a keyboard, and a pointing device. And so when I was a grad student, before I joined here, I started working on these shape displays. Here is an example of one of those. And the primary idea behind the shape display is that rather than only seeing, we could actually touch information, and we can also interact with that information over a distance. So we can start interacting with each other using our bodies and reconfiguring space. And so to me, when I first joined here in 2018, there were a couple of really inspiring challenges that had like kept me up a lot during my own grad years. And those were like partly technical, because we're like, you know, building shape displays is, oh, this one's a little loud, but you may hear in the background. I'm just gonna pause this for a moment. Oh, interesting. Okay. You may hear in the background, so the shape displays that I built and that a lot of people in my community built are usually quite bulky. So we're trying to think about future phones, future laptops, but what we're actually building is tables. They're also they're quite limited in terms of the shapes they can render. So what we see here is what we call 2.5D. So the shape display consists of a lot of pins that move up and down. So one challenge is how to make the shape rendering more expressive. So how to have more degrees of freedom, how to have shapes that could be compliant, that I can touch and deform, that maybe conform to my body, and that I can render at different scales, from the fingertip to objects that I hold in my hands to environments like this room. And then, of course, besides the shape output, or closely linked to it, is the mechanisms for rendering these shapes. So having them compact, compliant, hopefully silent. And then furthermore, besides these technical challenges, there's a big design challenge. And I think that's one of the major parts that I want to address in this talk. This idea of like, once we build a thing like that, or if we envision that we actually have these shape-changing, haptic, robotic interfaces, what do we actually do with them? How do we connect them to interactive media? And so what would be the design tools that are needed to inspire us in order to make that happen? A lot of us who here in the room has used like graphical user interface design tools like Figma, for instance. So that's one of the quite common ones for wireframing. So what would be the Figma of these shape-changing interfaces? And so that's essentially what I spent the last couple of years on, these thoughts. And I'm just gonna jump forward. And I want to acknowledge that, of course, this was together with my students. Here we see my current PhD students in the Thing Lab, some of whom are co-advised with Professor Elendo here, but also my prior collaborators. So this is very much collaborative research. And so the very first challenge that I was talking about is making shape displays more expressive. So Ryo Suzuki, who was a PhD student here at CU and is now a professor at the University of Calgary in the computer science department, was tackling this challenge of like, could we render shapes without overhangs? And so one approach to that, oops, is rather than having these pins that go straight up and down that push out of a shape display, could we actually use that shape display in order to manipulate objects that are on top of it? So think of this as a very like compact modular form of shape display that is 3D printed in almost real time. So we can have these shapes that come out of the display that we can then touch with our hands, pick up, manipulate, kind of like Lego. So similar to that, and then reuse again as we're interacting. So now what that means is we're not limited to shapes that just emerge out of the display surface. We actually use the display surface to make these reconfigurable objects that we can then interact with. And so this was a really inspiring first step to say, like, rather than trying to make these deformable surfaces, could we make something that is more modular in order to give both more expressive shape output, but also more expressive interaction possibilities, where I can start to reconfigure things. All of us know how to use Legos, and I've played with them. And so this idea of modularity led us to say, what about shape displays that, rather than being one big surface that assembles things, are composed out of an array of out of a series of modular robots, where each robot can actually change its shape. So the idea is, we have all these very simple, compact real actuators that were custom built. We put them on top of a small robot on a tabletop, and these robots can then deform in various dimensions, and also come together in order to form a shape display on demand. So to render shapes as we need them. And so here are a couple of examples of what you could do with that. So here we have a shape display that renders on demand when it comes to any type of, say, election data or any other map-based data I might be interested in. The chart is rendered physically. These robots could also just interact with static objects in the everyday environment. So both for rendering information, but also for just giving what we call dynamic affordances to these physical objects. So here, I like this example in particular because we have an object that was not computational before. This cup that didn't have any shape changing or other properties, but now these robots kind of give an affordance to the cup and say, you know, now you're allowed to drink it because it's not too hot anymore. So this idea, and I think that goes back to what we're thinking about when we talk about elastic spaces. This idea that we add this like level of dynamic elasticity to our everyday environment, and rethink of how we could work, play, and interact with the objects around us. And so earlier you saw a CAD application where we have like a physical instantiation of the model. Here you see that, you know, with these dynamic tools, something like CAD could happen in the physical world. So where we use this as a dynamic ruler. And so there are some technical parts to it in terms of like how these robots come together in order to render shapes, how they're controlled. And there's a lot of details that I'd be happy to answer if you have any questions about it. I've been meaning to say that at the beginning of the talk also, since you all seem like a very friendly crowd. Do feel free to chime in at any of these projects and ask questions about them. But so this idea of modular shape rendering, I was at the beginning showing we had this like dynamic space, like elastic space. So but this here is still, it's modular, it's dynamic, but it's still happening on a tabletop. So one idea and inspiration that came out of this project of rendering with these shape-changing swarm robots was, what if we could scale that up and make an environment that is dynamic, that we're actually inside. So here, this brings us to our next project. Thinking about scaling these up. Room Shift was a project where we're like, what if we could render a whole like dynamic media in a whole room? Now that's a tricky thing to accomplish. And so, oops. One issue I have, give me 1 second. I'm just gonna adjust. I realized I can't adjust the volume anymore once it's connected to the room scale audio. So let me spare you something that is too loud here. All right, make that subtle. There we go. Okay, that will allow me to talk over it as well. So room shift are room scale shape changing robots. They're able to move up and down. They're actually little iRobot Roombas that are tracked in a physical space and equipped with these custom built actuators, actually modified laundry racks from Target. And these robots are able to drive underneath objects, pick them up and move them about. The idea behind room shift is that in order to build a whole room that is dynamic is tricky and is hard to scale up. So what if we could have props that we move into place as we need them in order to show dynamic media and to be able to experience it? So what you see here with this robot is in virtual reality, we have a scene where we're experiencing a changing scene in virtual reality. And so as Rio is moving around in the room here, the robots, the swarm of robots, keep moving props so that whatever is in reach in terms of environment features can actually be touched by him. And so he gets dynamic feedback. And the idea is, say, in an architectural application, if we want to render a room and we see a chair in that room, we should actually be able to sit down in that chair. But then as we teleport or move to a different place and see another chair, or the location of objects has shifted, these robots are able to quickly adapt. And because they're a swarm of robots, they're even though each individual robot is quite slow, they're able to coordinate their actions in order to be faster, generate scenes faster by coordinating tasks between each other. So sometimes I may have a robot that renders a chair over here, and then as I teleport, another robot will come in with a similar chair in order to make a handoff. And so here you can see a simple VR scene, but what's fascinating about this one is that I'm actually able to experience and touch the furniture, the objects in that room. And this idea of like room scale robots that can change and reconfigure has led us to testing more, and has led to a more recent project that is headed by Sweeby Wang and David Hunter, where we're using the same robot and the same infrastructure for a training environment for astronauts. This was a project sponsored by NASA together with Diamond Age Technology. And the idea behind this one is, as we have a simulation environment where we may, for instance, need to pick up rock samples or interact with interfaces in an extravehicular activity, we are able to actually interact with real objects and real tools. And as those scenes keep reconfiguring, the robots keep reconfiguring the training environment. One thing that is interesting about this is not only are we able to like recreate scenes that in this room, we're also able to mimic larger environments. There is a technique in virtual reality that is very common called redirected walking. Now, redirected walking is essentially about being able to mimic a larger space, that is virtual by slowly guiding the user into walking, for instance, in circles rather than a straight path. Now, you can do that visually alone. And if you push the idea of redirected walking through these visuals, so you see as you're in virtual reality, you turn a little bit, and the physical turn of your body does not exactly correspond to the virtual turn that you're making. So what that means is you keep steering a little bit, and say, for instance, keep walking in a circle, keep getting steered towards a target. If that is visual steering by itself, we're kind of limited on how far we can push that, because at some point you get motion sick and things start to feel off. So having interactive distractors is usually quite useful in a redirected walking scenario. And so that's where haptics come in. This research project essentially was investigating how we can use these room scale robots in order to steer and to distract the user, so they would walk in what seems to be a larger environment, while at the same time being able to move about in the room. And this work is still ongoing, the studies for the redirected walking, but the results so far are pretty promising. And so we think that that's a really interesting use for robots to add haptics, dynamic haptics to VR, and thus make them not only more engaging, but also more scalable. And then we have one last kind of idea of how we could enrich these virtual elastic spaces in terms of room scale. And this again is a project by Ryo Suzuki called Lift Tiles, where we were looking at different actuation technologies. So the ones you've seen so far were solely electromechanical, so servos inside a robot. And so we are quite inspired by soft robotics and how we could employ those. So what you see here is a real actuator, where we use a pneumatic actuator that is combined with a constant force spring in order to make a tile that is quite compact and lightweight, but when hooked up to an air compressor and controlled by a computer, can generate quite drastic deformation. And so the reason this is called lift tiles is because we're literally envisioning making a room scale shape display where we're outfitting the floor with tiles that then deform through these pneumatics. Here you can see a prototype of lift tiles in VR. The idea again is that with these tiles, we could configure them also in various spaces. So they would not only be useful for, say, virtual reality. We could also do things like make reconfigurable architecture, where we have kind of spaces or room dividers that pop up on demand, and that can be reconfigured by the people inhabiting the space on demand. And so here you, for instance, see like an architectural feature that is being rendered on demand. And this idea of using like novel soft actuators in order to achieve a level of compliance and deformation was also explored by Fernando, who's a PhD student at Atlas, and was working together with the Keplinger lab in mechanical engineering to use this Hazel technology, which are soft actuators, in order to make silent, compliant shape change happen. And so the idea was that what's beautiful about these actuators is while they're a little bit tricky to control, they require high voltage electronics. They're very compact. As said, they're silent, and they allow for a lot of expressive shape output. So by combining different types of geometries, you can actually generate a lot of really interesting shape deformations that could lead to future shape displays that you can either that would fit inside a very compact handheld devices that would be deformable, say for deformable displays, and that could even be worn on the body. One kind of particularly interesting outcome of this work was a design tool that Fernando developed. And this was a plugin for Rhino, a 3D modeling software that some of you may be familiar with, where you can design how you want to what shapes of actuators you want, and then simulate what type of shape output you get based on the geometry that you design. And then automatically, or from that design tool, you could generate the CNC parts for actually fabricating. So for heat sealing, filling, creating the electrodes, and cutting the material in order to make these origami-like deformable structures. And so to us, this is really inspiring, this idea that, you know, you can take, say, a novel actuator, like we didn't develop the Hazel technology, but that you can take these advancements and then create the right tools for designers, for interaction designers, in order to create completely new and different applications, and then use that to feed back into the designs that mechanical engineers use. So I think that a lot of these tools we see as kind of a bridge between different communities and between designers. So that leads us to kind of this idea of design tools for elastic space. These tools for prototyping and co-design, and a lot of the current work kind of comes out of this motivation. This idea that, you know, designers have the ability to grasp technological changes, science and societal changes, and then convert them into objects and ideas that people can understand and use. And so this phrase by Paula Antonelli, I think, sums up really nicely why we need to engage designers in like science and technology as it is developed, not just kind of designers profiting from it as it trickles down later on. And so for me, the big question is like, what would be these design tools for like shape changing and for haptic user interfaces? Part of that comes from the frustration of having prototyped a lot of these interfaces myself, and also experiencing that in teaching. So here is like, say, when I teach a physical computing class, this would be like your standard kind of process, right? Where you sketch and ideate, then you prototype with electronics, so commonly with an Arduino or another microcontroller and an electronics kit, and then you start to test with your users. If you have, once you have your first functional prototype, then you go back to prototyping or ideating because something doesn't work. That would be the ideal process. But in my experience, very often, because this prototyping stage is very involved and complicated, most of the time, it is actually quite a linear process where people are getting stuck in the technical implementation, even of the first simple prototype. And then that's kind of where you end up. You're like, okay, this is what we have. We know that it should be better, but it's kind of hard to modify later on. So one question is like, how could we change that? The other one would be in terms of prototyping, shape-changing user interfaces. Here's, for instance, a prototype that is a video, like a stop-motion video. Before we built one of the higher resolution shape displays, we just like made this like stop-motion animation with just static props and the camera set up, and then like taking a photo after each frame, kind of what you see in stop-motion videos. Stop-motion movies. And that can be quite successful in conveying an idea, but you can't really user test anything with it. The idea is like, this is like essentially the video is the outcome of the product. You have these props, but you don't really engage the end user all that much in any interactive process. So the question is really, could we make something that replaces these or kind of in the early stage allows us to do more than just a sketch on a piece of paper and more than just a video prototype that we make, and where we actually test these user interfaces. And so in classic graphical user interfaces, there is actually low fidelity prototyping tools that are tried and tested and have been in use for quite a long time. So paper prototyping is one of them, right? You like make your app, say your phone app in this case, out of paper. You modify it, and then you actually sit in front of the user and run them through the paper prototype. And what's beautiful about this process and why I still like it so much, even though we have very powerful digital wireframing tools, is because it encourages the person that you test with, that you ideate with, to actually go in and participate as you test. The other kind of beautiful UI design tool is Wizard of Oz user testing, where you mimic a lot of the things that an interactive system would do. So this is one of the very earliest examples of a Wizard of Oz user test by IBM back in the 80s, where they were testing speech interfaces and mimicking that by just having another person sit in another room transcribing what you talk into a microphone, and thus like having, so to speak, a perfect speech recognition that wasn't available back then, and being able to actually test what that would mean in an office environment. So this idea of like these low fidelity UI design tools has inspired a range of projects. One of them called Wizard of Props, which is still ongoing. And the one idea is to, rather than use electronics to actually mimic how a robot or how room change would happen, what we instead do is we use people. So we do like a Wizard of Oz that is physical, and we combine that with virtual reality in order to have a virtual scene that is modified by a physical person. And so think about what you saw earlier with the shape-changing robots in the room that move about furniture. As long as the person is in VR, we can replace that robot with a person, move about the chair, and thus prototype very simply. So here's an example of what that would look like, this idea of like building props, combining that with CAD tool and with spatial sketching tools, and then user testing it and using that to facilitate the co-design process. So here is Mel, who was a student at Atlas, very good at prototyping in cardboard. And so she was creating props. And then once we have a number of props, like a robot here and the number of purposed objects, we start to sketch in that environment. This was a sketching software developed by Peter Gyuri and Karen Seng, both also former Atlas PhD students who now have graduated. And the idea here is that with these tools, we can rapidly create an environment that is both physical and virtual. So the example scenario here is a shape-changing room that also has a robot inside, something that would be very hard to create. And that would probably take us weeks, even with robotics knowledge. So we have sketched a low fidelity sketch of the furniture, of the environment, and now we're ready to user test. The idea is here we have a shape-changing room, so the person's waking up in their bed in the morning, and then this is what they see in virtual reality, and then they can interact with the object. So in this case, through gestures and speech, say I want the bed to transform, so the bed transforms, and so now we have this like beautiful micro apartment that suddenly has more space. And then in that space, we say now, like, you know, I'd like to have like a robot come in and bring a cup of coffee. And so again, we can test kind of the interactions, the behaviors of the robot, how they would react to speech commands, but we can actually always have this physicality. And we can actually touch and interact with all these objects and with the interfaces that are part of them. So this idea of like having kind of low fidelity, quick and easy sketches in order to design together. Has also led to this project called Designing Together, Miles Apart, led by Casey Hunt, a PhD student at Atlas. And the inspiration behind this project was when social distancing measures were in place during the pandemic. Everything, especially schooling, moved online, just what you saw in the very earliest slide in my talk. And that proved to be quite frustrating, not just for us, but especially also for kids. So we worked together with a team of students, designers called Kids Team, based at UW in Seattle. And they used to co-design together in the same room future interfaces, which was not possible anymore. And then as things moved online towards Zoom, that became quite frustrating for the children designers. So we started working on a new interface with them where we were like, could we bring physicality to this process? So rather than only being on Zoom and talking and using software to modify things, could we actually be in each other's space as much as possible? Could we share objects over a distance? And so the idea behind it, or the method was, we were engaging for 2 years with a team of 13 children designers aged 8 to 12 years old. There were a number of adult researchers and volunteers that rotated through this project in the course of 26 months to experiment and to design together with the kids what this idea of like being together over distance physically should mean. So one of the earliest kind of prototypes and ideas was rather than having Zoom the way we have it right now, where it's always like kind of like looking at your face straight up, could we have a simple intervention to just like be able to flip down a mirror and look down into what we call the task space? Because one thing that we realized is a lot of the kids were just frustrated being on Zoom all day, and so they didn't want to like after school also be on Zoom and have their camera on. So they would often like either turn off their cameras or just kind of like drop out of Zoom right away and just being like, this is boring. So we were like, you have the choice. You can either like, when we talk, switch to the face, or when you want to show something, or when we do an activity together, you can share your hands and share what you're doing in the space. So this here was, for instance, an activity where we're like making a little stadium out of Post-its, and everybody was doing that at home in their space. And so that suddenly that simple intervention already made quite a tremendous difference in terms of engagement and in like staying online. The second one was to also add not just having the mirror and being able to share objects. So the very first activities we did were just physical, like playing with Legos, crafting with cardboard, and sharing and seeing how you can share instructions as you make something. You want to share it with somebody and tell them how they can make that, for instance. The next step was to add robots to this. So the idea that you have these small tabletop robots, they're about the same size as the ShapeBots project I was showing earlier. Each kid has 2 of them. And you can either control these robots through an interface. We tested different types of interfaces to drive it around. You can also modify the robot, stick Legos on it, and change it. But furthermore, Casey wrote custom software to connect all of these robots through a web server, and to make also a custom Jitsi-based video conferencing app that would enable all the kids to be in the same space and to connect to each other's robots. And either say, I move my robot over here on the table, and yours moves synchronously, or I steer your robots directly. And so lots of interesting hijinks ensued, as you can imagine. Here you can just see like part of that on-screen interface where this was like controlling the robot. And so the idea was these sessions were quite open-ended, and it was a longitudinal study. So we kept going with the kids in terms of modifying both the interface, depending on what they told us should be done. So here are a couple of different iterations, for instance, of the software, of the functionality. One big thing, for instance, was the kids were like, we want like various buttons that should make the robot go into, say, a party mode where it starts to like flash lights and dance around randomly. I want to have like a shuffle and the spin mode, so I can like send something maybe akin to like emoticons, or you know, like celebratory dances at video games if you like score. And then we tried different activities of like partly competitive activities, where you try and like solve a maze, where you try and like play games like soccer. And these were all crafted by the kids, the environments, and they kept telling us what needs to change in terms of the software. So what does the controller need? And in addition to that, they also kept modifying the robots themselves. So having things like scoopers or attachments, for instance, that would allow you to draw with the robot. So the findings from those, not going to go into too many details, but I'd be happy to share more, is that the engagement through that physicality, the engagement actually did go up tremendously. We saw in all the recorded many hours of video data that we collected and analyzed and coded, that there was a lot more engagement and communication. What was also interesting, and I think that was like this whole project kind of started, one could say, as a solution to a problem that was very, very current, right? Like everybody was at home and we wanted to be together over a distance. But what we found is by being at home, a lot of new design parameters were actually added that were quite interesting and positive. So the social context of the home really shaped how the kids would collaborate with us and with each other. So by bringing in objects and pets from the home, by ideating, by bringing in their siblings, by also having to debug things by themselves when technology would break. It would be like, now we have to figure this out because I'm here by myself. So this idea of there was also a lot of assumptions that kind of kept breaking throughout the project. We would think that, especially at the beginning, as the software was like maturing, we're like, running into bugs, into connection problems. And so these recurring technical difficulties really showed us that like the value of longitudinal design, like of really engaging over a longer time and being able to not only solve that ourselves, but also have our children co-design partners become experts in the technology and being able to suggest and solve together with us. And so a lot of things, as said, we move towards improvisation on a structural level, where the idea was when things break, it becomes a feature, so to speak. And the kids were like very often rolling along with that. So this project has since then evolved in quite interesting ways in that now Kids Team is in person again, but as a remnant, and I think that's something that we see a lot in education, whether it's formal or informal, is there are in-person meetings that become hybrid by design. And that's actually very often a good thing in terms of like improving access two meetings like that. So a lot of kids could join that would be too far away in terms of like driving distance to actually come to the in-person meetings. Again, it also enriches because you actually bring in a lot of the improvisation from your home into the meeting. So it makes things fascinating and diverse and rich by design. So that's the project we've been most recently working on. This idea of how can these robots and how can sharing physicality be supported for or support hybrid meetings. And I think that's going to be something where even though we may not experience like purely online and socially distant scenarios anymore, pretty much all of these findings, I think, we can apply very, very well. But also we realized in the hybrid scenarios, we actually have to do a lot of adaptation. So this idea of like engaging directly with designers, and whether they're children designers or adult designers, has driven this platform for haptic design that Rancho, also a PhD student in the Thing Lab, has been developing. The idea behind this project called Emotitector is, it's quite an interesting finding, not ours, but we're very inspired by it, by Hertenstein et al., that you can communicate emotions only through touch. So what Hertenstein and their colleagues did was have people in a room, stick their hands through a curtain, and then you're not allowed to, communicate. You can't talk, you can't see each other. You only have access to the hand, and you can touch that hand. And then we were asking people to communicate a set of emotions through effective gestures, and then see whether they're able to decode those emotions successfully. And so it was actually quite surprising how good people are at decoding emotions. So there's a lot of expressivity that you can communicate through touch. And so the first hypothesis of this project was, if people can do it, could robots do it too? So could we communicate emotions and have kind of expressive touch just through robots? So Ram built a robot, this one here, that has 6 different tactors that are able to just convey kind of mimicking human touch behaviors. So shaking, pushing, patting, tapping, squeezing, and then software to control all of these in an expressive way. And so the research procedure was, we have these tactors, we have a testing device, and then we ran the first thing was to run a decoding study to just see, like, design gestures ourselves that we think would communicate expressive emotions, and then say, have a group of participants decode those gestures and see whether they can actually successfully do so. And that was the very first one. Then the second one was to invite designers to actually use this platform to design emotions, so emotional robotic touch. And emotions for us, that's like one very first stage of expressive touch, because we often have a concept of what emotions mean. So here you can see the device in action, and in the background you can actually see part of the software to drive that we used in the studies and that we used for designing this emotional touch. To us, one of the most interesting findings, and I'm gonna primarily focus on what the designers did. So those 11 designers that we just give them an emotion and say, like, try and convey sadness through this device without any other cues. That there was a lot of overlap in how people, in the parameters that people chose to convey these emotions with this device. So that was encouraging. The second one was we then asked the designers on like, what were the strategies? Like, how did you go about designing this touch? What did you actually think about as you were doing that? And also observe them and how they did that. So some designers will go around and like explore every tactor, try them out. Others were like immediately like, I know exactly what type of touch I want. I see a motor moving and I'm like, that's going to be the angry one. And I'm going to like change that. Or they would like start with touching themselves on their arm and try things out. We also realized that the metaphors that people used were very different. So they kind of moved away from interpersonal touch. There were some interpersonal touch where they were thinking about, you know, how they would touch a family member, a loved one, or a stranger, and think about how they would convey emotions. But a lot of things were like inanimate objects, were interacting with animals. So there were a lot of different metaphors that designers used. And then also how they reacted to the touch, both the touch that were like was pre-designed in the decoding study, but also in the touch as designers designed a haptic touch. They were actually or a haptic behavior. They would have different reactions to the touch. And so to us, that was really interesting because we kind of had these expectations that people would go about designing touch in very similar ways, that they would probably like start with interpersonal touch and mimicking that, interpersonal touch metaphors and mimicking those. And that turned out not to be the case. Yet, nonetheless, there was a lot of overlap in how people designed, even as they were thinking about different metaphors and as they decoded it. The other thing that we realized is by like sticking to this kind of like abstract form factor, so this what we call like otherness of robotic touch. You know, this is quite different from a hand touching you. The possibilities of how people were thinking and what metaphors and designs they used were quite broadened actually, and we thought that's quite a positive thing in that sense, and that led directly to this follow-up project, our next project called Tactobots, where we're like, could we have this be mobile so you can actually put it anywhere on your body, and could we use the lessons learned and how people approach touch, the different angles they come from, in order to design an interface on how they can design touch. So Tactobots was again a longitudinal study where we had a series of tactors that are mobile, that you can strap on your body, and the set of software that you can see here to control those tactors. And the idea is that it's a design-driven software. Again, we have like a set of different types of tactors you can choose from, for instance, to stroke, to tap, to shake and squeeze. We worked together with 13 designers, and each one of so there were 13 kits, and these were sent out all over the US and some in Europe to different designers, researchers, and artists who then worked with these tactors and had the time, pace, and space to work with them in their own labs and homes. And that was a lesson we learned from the Together Apart project, where we were like, this is really something that you can't do in a lab directly. It has to be people at home, or people that are in a setting that they choose, designers that are in a setting they choose. So this was the study procedure. It was sometimes between 2 weeks, sometimes like from 2 weeks to 6 months. We kind of gave the designers the freedom to choose themselves. And we had a whole number of interesting findings that came from this toolkit and from this experiment. I'm just gonna pick a couple of different ones. So one was that we had a few tactors that had absolutely no equivalent in terms of like you didn't really know what it was until you actually tried it out. Like this rub tactor, most designers and even haptics researchers that we engaged with were quite surprised and had like different ideas of what it would be. So some of them were like reminded by a rough cat tongue licking them. Others were thinking of goosebumps as it was rubbing them on their hand, and this was not just constricted to the hands. Actually, the designers went quite wild and were really tried out around the body to get different haptic sensations and responses. We also realized that the environment made a tremendous difference. And was enriching. So again, bringing in pets, traveling with the tactors, and the metaphors in touch design that emerged were again incredibly diverse. And what we realized is that so when it comes to these shape-changing haptic interfaces, we rely a lot on like preconceived notions of how we interact with the world, what we often call affordances, and the affordances of these tactors are physical in how they touch you, but we made very deliberate choices in the form factor that we gave them, and not making it try to mimic, say, a human hand or any other like kind of preconceived idea, and so that really led to a lot of alternative metaphors in how people were thinking from their own experiences, from everyday objects they encountered. And that also really inspired and changed how we changed the software to design the behavior of these tactors. And so this ongoing work is still happening. We're still decoding booklets that the designers were creating to ideate haptic interfaces. And we're working on the next generation of soft interfaces for haptics and shape change. That's a workshop that we're going to be running at WIST together with a number of professors at the end of October. And with that, I thank you very, very much. So I think go right ahead.
So this is great, fascinating work. I loved hearing about it. One thing I wanted to ask is throughout give examples of interactions that feel usually non-threatening.
Mm-hmm.
When I think of touch by certain people, certain relationships, or certainly with inanimate objects, I think of fear. We didn't talk about stress. We didn't say that. But what kind of experiences did you have across any of these many studies with ideas around fear of interacting with robots or whatever it might be?
So it's a really interesting question. This idea, and to paraphrase, like how do we deal with questions of like fear of the robot touching you? Will it hurt me, for instance? But also, touch is very loaded. Like there's a lot of questions of like, when is it appropriate to touch, for instance? A couple of different things around that. So one was very often in our designs, that was one reason why we, for instance, designed these transparent tops so you can kind of see what's going on inside, and also primed the designers in terms of like the activity and how they should approach, like how they should first try how this feels, and also encourage them to like be able to take this apart and check out what happens inside. So I think this level of transparency is quite necessary, but that doesn't fully answer your question. One really interesting finding that we had, and we call it here, let me just go to the slide again, this otherness of robotic touch, so that, you know, it touches you and it may feel like a person like squeezing you, but you know it's a robot, and you know that it's, you know, it also feels a little bit different, you know, it's more mechanical. People are actually a lot more open to the idea of being touched by a robot than by another person. And so even if say I wear you know, this interface, and you're the one who is actually pressing the button to say, like, you know, give me an effective squeeze, I'm actually open to that as long as it's the robot touching me, not the human directly. So on some level, interestingly enough, it is actually less fearful, so to speak, to be touched by a robot. Also because I have a certain level of control over it when I wear it.
It depends on who the person is who's delivering that message though.
That's definitely, I mean, it's very contextual. But having said that, like, if we go back to, like, say, a professional context, you know, beyond a handshake, there really aren't many touches that we exchange with the people around us, and that's probably quite a good thing in terms of all the negative workplace experiences that we may have. But then on the other hand, when you send me a text message and it vibrates in a pocket, like in a quite like intimate place, like on my body, I don't really have any negative association with that, because I can still, even though I still associate it with you as a person, so to speak, and I may actually get like a positive thing. I'm like, oh, somebody's thinking about me, but so in that sense, that still is, you know, there's a lot of otherness, and you know, we're not used to vibration as a haptic sensation from the everyday world. It's quite uncommon, except for like high frequency vibrations, as we like, you know, experience, like explore objects around us. But like, you know, the standard vibration cell phone, we're not used to. So that's quite different. Now the question is, it's also not very expressive. So the question for us as designers, as interface designers, is if we want to make haptics more interesting, can we push it towards more expressiveness, yet kind of still remain some of these properties that will not make it awkward and creepy? Or maybe in certain contexts, maybe they should. I mean, in the study, we definitely had like fear, disgust, sadness, and anger. So we were looking at negative emotions as well. Yeah.
Thank you.
Thank you.
I have one small question about the same topic. But how do you consider the question robotic in the cultural approach? I mean, people from US, different emotions and approach. People in Europe, people in Latin America, how do you consider this cultural?
So how do we approach and consider the cultural approach and cultural differences when it comes to like, say, in certain countries, like, oh, and you know, a kiss on the cheek is normal. In the US, maybe less so. And so I haven't talked much about the cultural background of the designers that were part of this study, also because most of them were in the US. So in that sense, this is a very kind of American perspective, even though the designers were international, but, you know, have been studying and working in the US, in the Western world. So again, it kind of touches back to this question of do we think that when a robot touches us, and what type of touch we experience. Do we think of it as the direct cultural equivalent of a human touch? In our experience, that's a no. Like, there's actually quite a big difference, but also that's because, and I will probably get a lot of interesting questions and feedback from the HRI community, because I think in human-robot interaction, a lot of the robots actually have you know, very much human-like features. So we have like a humanoid robot. And in the interfaces that we built, both in the shape-changing rooms and in the variables, we deliberately do not use any like human resemblance, so to speak. So maybe if a humanoid robot would come up and squeeze me, I would have quite a different reaction than if I have a variable that delivers a similar squeeze sensation. But I do think that that also speaks to the cultural differences that you were mentioning. I don't want to make too bold a statement here just because I actually don't know. But it's...
I mean, you can transmit emotion in one way, and the system is in way. So I am just putting the human factor in the center. Not about the perception chain that then the background.
I mean, it's also super fascinating because it brings us back to like a lot of the interface design that is well explored is in graphical user interfaces, right? And so when I teach like introduction to human-computer interaction, one like thing is like, you know, layout, like just how do you design an interface? What colors do you use? How do you do spacing? Like some graphic design. And there's always the like slide in the deck that is about cultural differences of colors. It's like, be careful because, you know, white in Western culture means it's a wedding. But then you go to another culture and it may mean funeral, and likewise, you know, there's like red is anger, though the interesting part is that very often that is quite debated in graphical user interface design, and that very often in a lot of contexts we're thinking about cultural contexts, but then when it comes to like symbolic meaning of, say, colors, people are actually quite flexible about it. And you know, I don't see like, you know, a black slide background and think of like a funeral right away. Or when I have color-coded information and say like navigation, you know, 7 different colors, I don't necessarily associate that like one is happier than the other. So I think this balance between like symbolic meaning and emotional and cultural meaning, and what balance we give it through context, that's actually where it gets really interesting. And I think it's totally underexplored when it comes to haptics, robotics, and shape change. Thank you. Thank you.